Hello, everyone, and welcome to a rather short stream here today. A continuation of the DirectX tutorial slash beginner series, where I go through the steps of creating a DirectX application. Let me just set up some stuff here. Today will be a rather short stream since I have somewhere else I need to be in maybe an hour or so. So originally I thought that the next step, the next logical step, would be to create some buffers on the GPU, but well, I think that would probably, or rather, I thought originally that I wanted to do a pipeline stream, since they are a really important part of DirectX 12. But since I have limited time, I think that the buffers and the whole thing about uploading data to the GPU is probably a better topic. It's also one that can be divided into subtopics, since a pipeline is more something that you do an entire episode about in combination with the so-called root signature, uh, which are probably a bit more um, elaborate pieces of. Hello, welcome. Which are probably more elaborate pieces of the actual pipeline. Or rather the rendering process itself. So yeah, since we have limited time, I'll be doing a video on resource allocation and uploading. Maybe not so much allocations, as we will use a simplification to handle that, but we will do the actual buffer creation. Thank you very much. I have limited time today, so I won't be chatting too much, because I just wanted to squeeze in an episode before I had to go do something else. I just came home from work. Yeah. All right. Maybe we should get going then. Let me see. Okay. I think I'm probably set here. Let me see. Yeah, if we have more time, I'll probably do the root signature as well in a different episode, even though I prefer to do them in combination with the pipeline. All right, I'll start the recording in a sec. Hello everyone and welcome to this next episode / installment of the beginner tutorial on how to do your first DirectX 12 application in C++. Um, Last episode we did some final implementation on the command queue and the command list. We also did some weird stuff here that I might not have elaborated properly on in our update step. I will return to that shortly. As per always, this is part of a live stream. I might be doing more episodes um, um, if we have the time. Hello and welcome. I will be answering questions at the end of each video in terms of the viewers who watched the live stream. If you have questions or anything related to this content, feel free to leave a comment if you watch it in the future. All right. Today we're going to do some buffer allocation. Some buffer allocation on the GPU. We will be discussing that a bit. But let me first recap a bit on what we did during the last episode here, which I may not have explained properly. We initialized the swap chain with currently two buffers, which is created during the get buffer call to the swap chain itself, and we store them in some com pointers here. We also grab our descriptor heap starting position in terms of the CPU address and update the pointer for each of those to our the appropriate offset into that heap. So we make the swap chain allocate some render targets. It does it in terms of its own description, and these resources get allocated. We can also deallocate them by dropping the buffers. They are initialized as buffers are per standard in terms of the swap chain. And that means that they are created in a state that is both common and present, which means that the buffer is created in a present state, meaning that it can only be used to present something. That is a problem if we want to render to it. So DirectX 12 handles that by using resource barriers that controls the state of each resource. Is it something that we can write to? Is it something that we can only read from? Is it something that we can both write and read from? Is it something that the swap chain can use for a percent? Is it something that the pipeline can use for a render target? And so on. So whenever we want to render something to a render target bound to the swap chain, we have to make sure that it is in a render target state. So each draw call starts with controlling the state of the current back buffer, meaning the one that is not shown on the screen but is in the opposite side of the two buffers that are in our swap chain. One is on the screen and one is in the so-called back buffer, remember? And you could also have several back buffers, more than one. But we have to make sure that we can actually use the current back buffer as a render target. So we create a barrier. that we submit to our graphics command list. We record that command. Remember, this command simply just reinterprets our command list as a graphics command list. We created that method last time. It's just an inline method that returns a pointer to the same pointer as the underlying object. And we tell it to create a resource barrier, only one resource barrier with the description that we just specified. We then, for testing of this application, want to show that the swap chain actually does something. So we decided that we want to clear the current render target to a specified color as proof of our drawing. We therefore need to find the handle slash memory address of our render target. We ask the swap chain to fetch us that, depending on what is the current buffer. And we record another command to our graphics command list, which is clear render target view at the specified handle and the specified color. We then want to be able to show that on the screen, and we do that by creating another barrier, which will also target the current buffer, but we want to switch the state from a render target to the present state. We record that command, and now we're done recording commands, at least for now. This means that we will close our command list and send it off to execution on our command queue. We've created a wrapper that calls the execute command list method and increases our fence value. And this is really important. It's a intricate part of DirectX 12. You need to get to know the fences and how fences work and how command queues work with fences. It's highly important since it's abstracted away in a lot of more beginner-friendly APIs. So we increase the current fence value for our collection of commands, meaning that whenever these commands are done, we expect the fence, which is just a synchronization object, to have that certain value. We also tell the command queue that it needs to tell this fence, whenever I'm done, you will have this value. So this method here makes sure that there are synchronization steps available both for the command queue and for the CPU. We execute the commands whenever the back buffer is ready to be presented. Hello, welcome, and thank you. We will call that. In case our resources are in use, we simply need to wait for the fence of the command queue to have a value that is equal to our currently expected fence value when this frame here is done. Unless it's not, we pause the CPU thread. Whenever we're done, we can safely reset our command allocator, which holds all the commands, and our command list as well, and open it for registration of new commands. And we can do this over and over and over. This is basically a loop that, hello buddy, welcome. So the only thing that we need to make sure is that we don't call this sure thing I do, of course, haven't forgotten. I will never forget. Yeah, so that's it. That's basically what we did last episode. We also made sure that whenever we want to close our application, that we we've kind of flushed the command queue for commands and bound resources so that everything is ready to be released and nothing is referenced in terms of execution of different command list calls. So therefore we need to sort of create empty frames that we wait for, or at least tell the command queue to do. By increasing the fence. When we've done that, we can release our swap chain, which will, let's see, maybe I shouldn't reset here first. Maybe I should call reset last here. But it will drop the buffers, it will reset its heap, descriptor heap, and it will release itself. And then we do the same thing. Okay, enough blabbering here. We will now turn our heads to, let me see, maybe I should end the recording here for this part of the episode, and just call it a short recap episode, and then move on to the buffer stuff. Yeah, I'll do that shortly. All right, welcome to the next episode of the beginner tutorial series, where we go through the steps of creating your first DirectX 12 application in C++. Last episode was sort of a recap episode, since I don't think that in my rush I explained it properly what we were doing. In this episode we will be creating some buffers that we can use to store data on the GPU. Since DirectX handles buffers in a way that allows any resource to be any type almost any time, we need to we can create a wrapper for a generalized resource. We will create a resource folder here and create a wrapper for a D12 resource. We will of course create a what do you call it? A class here that will, as per usual, you almost know the drill, will inherit from the com pointer, and then we'll wrap a resource interface. We will allow our system to create a empty resource. Resources should be possible to allocate in certain sizes. It will always require a device. Let me show you, if you don't trust me. Whoops. And as you can see here, it's not only called create resource, it's called create committed resource. It creates both a resource and an implicit heap, such that the heap is big enough to contain the entire resource, and the resource is mapped to the heap. This means that this method here creates a heap allocation on the GPU, which the resource will reside in. You can do more interesting things with the memory management of DirectX 12. You can create placed resources, which requires that you predefine a certain heap and a certain alignment in terms of the resource. You could also do virtual resources. I think they are called reserved resources. Yeah, reserved and placed. So you could basically do different stuff. For ease of use, we will be creating the committed resource method. Heap management is probably a bit more of an advanced programmer topic. It's basically like any memory allocator. So if you know how to write a memory allocator from scratch, in terms of CPU memory, you will have no trouble implementing something like your own heap system in terms of the GPU. Just be mindful that heaps are of different types. We will return to that not too far out in the future. But this means that we would probably like something about some information about, about the number of bytes we want to allocate. And as I've mentioned, there are different heaps. You need to specify a heap. You might not have seen it in the documentation, but we actually do need to specify which heap this should reside in. Let's see here. Heap properties, we need to fill out a descriptor here for the heap. Since it creates the implicit heap, we need to give it instruction about how the heap will function. We also need to set some heap flags. And then, of course, we need to do the resource descriptor. And we also need to set a resource state. When you create a resource together on a resource heap, upload heap, we need to set it to this state. Let's see, generic read. Doesn't say anything about that. Generic read. Let's see, do we have any interesting states here? No, not really. Well, I guess there are a lot of different interesting types, but anyway. Read-only states, read-only states. write-only states, read-only. Well, we should transition resources to whatever needed states. We should probably get into that in a future episode. But yeah, let's do a default state. Generic the 3D12 resource state. Yeah, we want to be able to specify the default state, or rather initial state here, since whenever we allocate a buffer, we need to specify that, since it depends on the heap type as well. We could do interpretation for it, but maybe we want to initialize something in a different state. As you can see, the upload heap needs a specific type, and the readback heap needs a specific type, but other than that, we are probably free to do whatever we want. And I say probably because I am not 100% certain, but anyway, we will set up an initializer method here, and I forgot the namespace, which means I'm on the verge to go insane here. All right. So our create committed resource returns a age resource, so we can use our evaluate method here, and we can tell our device to create a committed resource, and we want the heap properties, the 3D12 heap properties, and we will initialize those as 0. The type will, excuse me, be our heap type. There are some other flags here. The node mask is of course 0, since we do not have dual GPU. The visible node mask is also 0 because we do not have any dual GPU set up here. Then we need to set a CPU page property. We have these not available, unknown, write back, combine. For now, we will just use unknown. Trust me on that one. You can always look it up in the documentation. Then we need the memory pool reference that will, excuse me, also be set to unknown. Let's see. And we will not set any heap flags. All buffers and textures. Only buffers. Shader atomics, not zeroed. Uh, Keep flag none. Next, we need to create a resource description. As you can see here, we will create a resource description. And we will have to specify some information inside that resource description. We will need to specify the dimensions of the resources. We need to specify an alignment on the heap, a width and a height, and depth or array size, meaning for 3D resources we have array sizes. MIP levels are for textures. MIPs are just lower quality representations of, for instance, a texture. We need to specify a format. We need to of course, set a sampler. We won't be providing support for multi-sampling in this resource, so that will not matter. We need to specify a layout here. For a buffer, that's usually, as far as I remember, a row major. All right, so we need to create the description here. We need to specify the dimension. We have these possibilities. We will create a buffer. We could create a 1D texture, a 2D texture, 3D texture, or something completely unknown, which will just contain data. We will create a buffer. If we specify the alignment as 0, we will get the alignment. Our width of this buffer will be the number of bytes. Since this is not a 2D buffer, we can do one continuous allocation of memory, and we simply don't need any height other than one row. The resource description here will be we will fetch the depth or array size. We will only have one in terms of depth. The MIP levels will be 1. We will not be creating any sub-resources here. The format will simply be unknown. We don't care. We will only care about the bytes themselves. So therefore, we do not specify a format. Bytes are bytes. It's up to the programmer to keep track on what is stored inside the buffers. We will do the sampling, which will be a count of 1 and a quality of 0. Since we're not doing sampling, we will do our layout, which is swizzle, undefined swizzle, row major. It's like we have one row and we want to interpret it as a row. We do not want any flags. Therefore, we set it to none. All right. We pass in a reference to our resource description here. I think this one also needs to be a reference. We pass in our initial state. We don't care about the clear value. I think we could set that to null. And then we need somewhere to store it. And you know where we want to store it. We want to store it on our com pointer from this from which this class inherits. We will send an error message if we do not succeed. Let's see, too many arguments in function call. So we do let's see, this one. Oh, should end here. There we go. All right, so this is the initialization of our resource. Since we would like to be able to allocate a resource of a certain size, we will do some helpers here. We will define a kilobyte macro where we take our x and we parenthesize our x so we can do an expression, and we multiply it by 1024. Since 1 byte is 1024th of a kilobyte. All right, so now we of course need to create the good old release function here. Excuse me, just a second. And that will of course check if we have a pointer here. We will call reset. And we will also create a destructor, since when this goes out of scope, we would like for it to automatically call the release function. All right. Inside our renderer API, we would like to be able to create a resource here. Did I not store it? Oh, I didn't move it. There we go. We want to store, yeah, let's say that we want a so-called dynamic vertex buffer. And I'll get back to what that means. Whoops. D12 resource. Can't I spell it correctly? Why not? Let me see. Yeah. Resource. I probably didn't spell it correctly. Anyway, we create our resource here. And the reason why I call it dynamic is because we will create it on the upload heap. And the reason why we will create it on the upload heap and not the default heap is because, let's see, kilobytes, 16 kilobytes here. And we need to pass in our D3D12 resource heap type upload, and remember what our documentation said. The resource state needs to be generic for that. Generic read for that. Let's see. Too few arguments. I'm not sure that that is true. Maybe it doesn't like this. I have included the helper inside my PCH here. Huh? Let's do like this. Let's do 16 here. Well, too few arguments in function call. Now that is weird. Why does the macro not want to accept that? Whoops. I added a semicolon. That's a bad habit. Anyway, and we can of course parenthesize this in case we want to do an expression instead. All right, we want to allocate 16 kilobytes on the default, or rather the upload heap, with the state of generic read when we initialize our application. A smart trick here is that you can name your buffers. If you get the pointer to the underlying interface, you can set the name. Dynamic vertex buffer. And this needs to be a literal. A white character buffer. All right. The reason why we do it on the upload heap is because the upload heap is a place where the CPU can always access. The generally the desktop platforms have kind of like 3 to 4 different memory locations. We have only CPU, default RAM / cache. We have a only GPU, which is the default heap on the GPU. Video RAM. And then we have shared CPU and GPU with read write for all. It's still stored on the GPU. Then you have the readback memory, which is primarily on the GPU with read from the CPU. In terms of speed and safety, This is, of course, the most safe for the GPU to use because the CPU can't just write to it. The CPU can only create it through the DirectX API. But you need to upload the information to this kind of heap here. This is allocated in a shared memory location, which allows for the CPU to read and write, but it comes with the expense of speed. It's also stored on the GPU, it's just handled differently. All right. The last part is something that they changed in DirectX Ultimate. They did more work on the shared memory model between the CPU and GPU. So yeah, I can't actually recall what they did of changes. Did to the changes. Let's see. The readback type heap here is yeah. As you can see here, the default heap gives the most bandwidth for the GPU, but it cannot provide the CPU access. This is a heap used for uploading. The CPU has access optimized for uploading to the GPU, but doesn't get the maximum bandwidth for the GPU. It's best for CPU write once, GPU read data once. Yeah. And you need to monitor whether it's faster to copy the data to a default heap from the upload heap versus reading the data itself from the upload heap. We cannot change the resource state. We shouldn't probably do any reads to it from the CPU. Therefore, you shouldn't use it for and we can also upload some dynamic data. So yeah, the reason why we chose the default upload heap here is because the CPU can access it and write to it, and it's also the first step if you ever wanted something to be uploaded to the default heap. You would have to create a resource on the upload heap and then also a resource uh, on the default heap, and then you would use your CPU to upload the data to the upload heap, and then tell the GPU through the command lists or a separate command queue with the copy type that you wanted this data transferred to the default heap. So that's why we create this resource first. You could, as you saw here, create dynamic data that is uploaded fairly dynamically and read by every pixel or vertex. In terms of a constant buffer. Generally, you would like vertex buffers to be on the default heap, since it's faster in terms of read or write ability for the GPU. And since the vertex buffers are used very often for a lot of computations, you would prefer to do that. Anyway, we have initialized our resource here. I will show you the effect of our construction here. We will, of course, need to release the resource when we are done. But I will compile this, and I will show you one neat little trick in terms of checking that your stuff actually works. We will use NVIDIA Insight. Let's see, for this. And let's see, we will swap to our project here. And we will launch NVIDIA Insight, which is a application that is used for graphics debugging. I will press F11 and record this frame. We will get a lot of different information here that is probably a bit overwhelming, but we can enter our frame debugger here and access our resources. We will see what resources our system has allocated. And we see that we actually have a dynamic vertex buffer. So our system created the buffer. We have a size of 16 kilobytes, which was approximately what we asked for. I think the minimum alignment is somewhere around 16 kilobytes, so that's probably why it's 16.4. But yeah, we created our buffer, and now we can look at the contents of our buffer. But how do we know how to actually store data in our buffer? Well, I'll show you. I'll also show you shortly in RenderDoc, just in case you use that. You select your application here, and you enable that you want to reference all resources here, and you launch your application, and you press F12 here. In NVIDIA, it was F11. And you can see here in our list, maybe it's too small for you to read, we also have the resource here. We can push the button read contents, and we can also access our buffer. Nothing is uploaded yet, but we will fix that immediately. All right. Let's see here. We want some information in terms of our renderer here. We want a header file that is used to define some types, render data types, let's call it that, and we will namespace the engine here. And then we also want to sub namespace this, because we might have overlapping types. We will create a struct. Oh, and I forgot, we will be using the DirectX math library for this. since the math library in DirectX simply provides all we need in terms of math to get everything up and running. So therefore we will include that. We will make sure that this includes our PCH file here. And our renderer, let's see, API will also use this type system, render data types. And let's say we want to create a vertex with a vector. Let's see, can we find a vector type? XM color, XM float, 3x3, XM vector. I know that is intrinsic types. Okay, so we will do the XM float 3, where we give it a position, which will be initialized as 0. And we would also like a color for our vertex. We would like for it to be green. And have an alpha of 1. Okay, so now in our render namespace, we have a certain data type that is a data container. Let's see, I specified one float too many here. Wait a minute, this is the initializer. I don't want it to be anything other than black initially, but the alpha is still fine. So let's say that we wanted to create a render vertex. Let's use the namespace of our renderer here, using namespace vertex, or rather a render. And now we can simply type vertex. Vertex data, and we want to set the vertex data, our position here, to be maybe an x of 1, a y of 5, and a c of 3. And then we want our color to be green, as I mentioned. So we do like that, and we do an alpha like this. Then we have this data available. We would like to store it as the first vertex of our buffer. So the resources, the original interface of DirectX actually has a function called map. The map function takes whatever sub-resource we want to map. It takes the range. I think 0 is usually the entire range, and it wants a pointer to store the data in. Let's call this destination, which will be a null pointer initially, and we will reference the destination here during our map function. Now we have mapped this address on the CPU to whatever address this has on the shared memory between the CPU and GPU. Now this pointer points to the start of this resource. Therefore, we can do a memcopy, and we our destination, of course. We want to copy from our vertex data, and we want to copy the amount of bytes that is equal to our vertex data structure. And then when we are done, we can unmap the whole thing. There we go. So if everything was done correctly, we can now use our debugging utilities to check if we actually uploaded anything to our buffer. Remember, the CPU can access the upload heap, so everything should be fine. We will use RenderDoc this time because it's not a specific graphics vendor, and people probably like this one. I need to get used to it. Anyway, hello, welcome. And if we click launch here and capture our frame here and access our information here, we know that our dynamic vertex buffer was here. We can open the contents, and you might be able to see that this is no longer 0. We can create an object layout down here by specifying, well, the first component is a float 3, the second component is a float 4, and we want to apply that. As you can see here, the first row in our buffer, it holds a x value of 1, a y value of 5, a z value of 3, and the color green with an alpha of 1. So this actually corresponds directly to this upload here from the CPU. So whenever you want to upload something to the actual GPU heap, you need to use this method, copy all your data into something on the upload heap, and then we will in the future do another call that makes sure that you transfer this information over to the default heap. But this is basically already uploaded to the GPU, and it's possible to read as soon as this is done. Therefore, whenever we set up our pipeline together with our root signature in our next episode, we will be in reach of actually drawing something. The next episode will be a bit long and will entail a lot of different explanations, but once we get a grasp of the pipeline and root signature stuff in terms of DirectX, and at least know how to set up a default pipeline, a simple pipeline, we will actually be able to draw things to our screen that is not just a simple color like the clear color here. So yeah, I expect the next episode to be really interesting in terms of actually using DirectX 12, since we actually don't need to do more setup. If we want to do something more advanced, like render something in 3D, of course we have to do further setup, but it's not that much in terms of, excuse me, in terms of getting started with doing 3D drawing. So within potentially 3 episodes, we could do 3D drawings to our screen. All right. I do not have any more time for today. So this is what I was able to do in this time span. I will be answering questions if there are any. Otherwise, I will have to end the stream shortly. And of course, I will upload the changes here, and they will be available at the GitHub repo shortly thereafter. So far, there was an question in regards to OBS, but yeah, I'll answer Karim um, somewhere else. Yeah, okay. Well, hopefully you found it helpful, entertaining, or maybe just inspirational. DirectX 12 is not super hard, so therefore, if you stick with it, you should be able to learn it. And if you want to learn Vulkan or something more like DirectX 12, it will be a great stepping stone. All right, if you found it helpful, inspirational, entertaining, or something else entirely, maybe just a little bit worth your time, well, then leave a comment, like, or subscription. You can always watch the video archive, and you're welcome during my streams in terms of when I do my own project in terms of game development. If you have any hopes that this tutorial series does any particular subject in the future, let me know that you have interest for it. I will consider accommodating your wishes if there are enough viewers that actually want some tutorial-like contents about a certain topic. All right, thanks for tuning in. Stay strong, stay passionate, and take care. I love you all, and thanks for the 100 subs that we achieved today. My greatest gratitude goes out to every single one of you. All right, much love. Peace out.